Why can DeepSeek run so much faster and cheaper than models its size should allow? Because it's not actually running the whole model at once. And that single design decision changes everything about how inference works. Inference is what happens when an AI model generates a response. You send a prompt, the model processes it, and tokens come back one at a time. The problem is that for large language models, this process is expensive. It demands enormous amounts of memory and compute for every single token generated. DeepSeek's engineering team built several specific techniques into models like DeepSeek R1 to make inference dramatically more efficient. Think of it like a restaurant kitchen that only fires up the stations it needs for your specific order, instead of running every burner at full heat all night. This matters the moment you try to deploy an LLM in the real world. A team running a customer support assistant suddenly discovers their GPU memory is exhausted after 50 concurrent users. A developer trying to run an LLM locally hits a wall because the model won't fit in RAM. A company's cloud inference bill comes back 3 times higher than the prototype suggested. These aren't edge cases, they're the standard experience of anyone moving from experimenting with AI to actually shipping it. Understanding how inference efficiency work, specifically how DeepSeek approaches it, tells you exactly why some deployments collapse under load while others scale cleanly. The architecture decisions made before training determines your ceiling at inference time. DeepSeek uses 3 techniques working together that most models don't combine this way. The first is mixture of experts, usually abbreviated MOE. Instead of one massive neural network where every parameter activates for every token, a MOE model routes each token through a small subset of specialized subnetworks called experts. DeepSeek R1 has a large total parameter count, but at inference time, only a fraction of those parameters are active for any given token. Less compute per token, lower memory bandwidth pressure, faster generation. The second technique is multi-head latent attention, which is DeepSeek's approach to compressing the KV cache. The KV cache, key value cache, stores intermediate computations from earlier in a conversation so the model doesn't recompute them from scratch with every new token. The problem is this cache grows with context length and consumes serious GPU memory. DeepSeek compresses the representations stored in the KV cache into a lower dimensional latent space before caching them, then expands them back when needed. The result is dramatically smaller cache footprint without meaningful loss in output quality. The third piece is speculative decoding support. A smaller draft model generates several candidate tokens quickly. Then the full model verifies them in parallel, rather than generating one token at a time sequentially. When the draft model guesses right, which it does often for predictable text, you get multiple tokens for the cost of roughly one. These 3 things compound: fewer active parameters per token, smaller KV cache per token, and batched verification instead of sequential generation. If this kind of deep technical design is what you want to actually understand, Stack Future covers one concept like this every day. Say you're self-hosting DeepSeek R1 using Allama on a machine with 24 gigabytes of RAM. You run Allama run DeepSeek R1 32B, and the model loads, but generation is slow and you're seeing warnings about memory pressure during longer conversations. The problem is almost always the KV cache expanding as context grows. Allama exposes a configuration parameter called numCTX, which controls the context window size and directly controls how large the KV cache can get, reducing it from the default 4096 to 2048 with Allama run DeepSeek R1 32B. Parameter numCTX 2048 immediately reduces peak memory consumption. That's the KV cache compression at work, or in this case, you constraining it. Understanding that the cache is the bottleneck tells you exactly which dial to turn instead of guessing. Teams that understand MOE activation patterns also learn to batch similar length prompts together, because uneven sequence lengths create padding overhead that wastes the efficiency gains MOE provides. DeepSeek's inference efficiency comes from 3 specific compounding designs: sparse expert activation through MOE, KV cache compression through latent attention, and speculative decoding. Together, they explain why the model punches above its weight in both speed and memory, and why understanding your inference bottleneck tells you exactly how to fix it. If this helped something click for you, hitting the like button genuinely helps this channel reach people who'd find it useful.